Okay, so we have the recording going. I got to resize my window here just a second while I resize this. Yep, okay. I think that's pretty good. Okay, wonderful. So we've got today, June 29th. Let's start with some announcements. So this week, I'm going to have some special office hours because we are affected by a holiday. The July 4th holiday is officially observed on the 3rd of July this year. So that affects us. So let's begin by talking about our schedule this week. And of course, looking ahead to Friday of next week, we have our first midterm exam. It's kind of sneaking up on us, but yeah, it's out there. It's at the end of the 3rd week of the course. It's an 8-week course, so it's natural to have a midterm at the end of the 3rd week. It's just like having a midterm at the end of the 6th week for a regular semester. Okay, so we'll talk more about that. Basically, the midterm is going to cover chapters 5, 6, and 7 with the deletion of a few sections. So it's 5, 6, and 7, and then delete a few sections. I will publish a document telling you exactly what to study for the midterm. Okay, so first of all, let's talk about our homework schedule and correspondingly office hours. Okay, so homework 2, right? This is important to us because homework 2 is, it has been published. Oh, let me remark, I have uploaded the solutions to homework number 1. So you go to B courses, you go to the folder for homework number 1, and the solutions are available there so you can look at the solutions. This is part of the learning process after you've been thinking intensively about these problems, then have a look at the solutions. Okay, so let's talk about the homework schedule. Homework 2 was posted some time ago. And what else can we say? The due date. Yeah, this is a special due date, Wednesday, right? You know, homework due 2 is due Wednesday. That's special, and that's the motivation for these special office hours. So I'll have office hours Tuesday, that's tomorrow, 8 p.m. to 9 p.m. Then Wednesday, 10 a.m. to 11 a.m. Then I'll have one more office hour later in the week because we will have yet another homework assignment. So that 3rd office hour is to be determined. I'll determine that one later. Okay. So we got that. Oh, homework 2, I will publish some more hints. I will publish some more hints. If you look at the homework 2 folder, you see a couple documents in there, helpful documents, and I will publish some more helpful documents. Okay, so that's important to say because again, taking Physics 105 during the summer is very challenging. We have only 8 weeks to cover a huge amount of material. This is very challenging. So as you know, the pace is very rapid and it basically requires you to constantly be working on the course. All right, so what we're gonna do now is resume our discussion of chapter 6. Furthermore, let's look ahead to chapter 7 where we start doing physics. And in doing this, this will help to clarify some of the confusing points. We'll talk about, we're going to revisit some of the confusing points. Okay, so here is a table. We're going to draw a table. And this overview, this table will give us an overview of the many kind of notational issues which are crucial. Okay, so notation, this is our choice of symbols. How do we express these mathematical ideas, which are rather complicated? And this will be a very useful table to help us to keep track of all this. So first of all, chapter 6 The main emphasis here will be a comparison between chapter 6 and chapter 7, okay? And so roughly speaking, we can say chapter 6 was devoted to math, chapter 7 will go into physics. So I'll put that here. This is kind of a rough overview of what we're doing. Chapter 6, pure mathematics. Okay, and here's what we're going to do in our table. Let's remind ourselves what was the preferred notation for the independent variable, the dependent variable, and then the function in our variational principle. Okay, and this will be useful to keep track of all these variables. So in chapter 6, for most of the chapter, the independent variable is x. The dependent variable, right? The dependent variable is y, and so it really would be best to write it like so. In my lecture notes, I'll publish it slightly different. I'll put a little remark here. This will be an inset. This is an inset box. So if the independent variable is x, if the dependent variable is y, then we will be speaking of the function y of x. So this is a little inset remark here, okay? This is what it means for y to be the dependent variable. Okay, and finally the function that we work with throughout chapter 6 now, variational principles. There's this function, and in chapter 6, it's called f. So I'll just put that there parenthetically. Okay, so these are some of the notational highlights of chapter 6. As you recall, at the end of our lecture, at the end of our last lecture, we had a certain role reversal. This introduced an additional layer of confusion into something that was already very complicated, but I wanted to discuss the role reversal because Taylor, the author of the book, does this role reversal. So I'll include a line in the table for that too. Okay, so these are the 3 table headings. So let's talk about chapter 6 with the role reversal. Okay. So we're going to talk about chapter 6 with the role reversal. We have to do this because this occurs within chapter 6. Within the discussion in chapter 6, there's a role reversal. And then the third entry in our table will be chapter 7. And this is where we start doing physics. Okay, so this is going to be a very handy table here to keep track of everything. Where have we been? Where are we going? Etc. So chapter 6 with the role reversal, at the end of our last lecture, this variable y was the independent variable, and the variable x was the dependent variable. And so the little inset box here, x is a function of y. That's a little inset box because really the dependent variable is just x. Okay, and the function is now, you reverse the roles. So it's going to be x prime. It's understood that x prime is the derivative of x with respect to y and y. So this was the role reversal. Again, the second entry, the second line in our table here is just to help clarify that role reversal. And so let's talk about the physics. This will really help to clarify everything. Okay, so the independent variable is the time t. The dependent variable, we have a bunch of them. For one-dimensional motion, you would have x. If it's a three-dimensional problem, you know, we like to use this vector r, which encompasses it's x comma y comma z. So it's all three coordinates. It's a point, three-dimensional space. And then later in the course, we'll have these generalized coordinates q. So again, the inset boxes here would be x as a function of time. For a one-dimensional problem, you're solving for x as a function of time. For a three-dimensional problem, you have r, the vector r. I'm writing pretty small, but I think with modern high-resolution technology, it should be no problem. And then we'll have this notion of a generalized coordinate q, so q of t. And the function, this is the fun part. Here's where we introduce the Lagrangian. This is the famous function of the Lagrangian formulation of classical mechanics. And this is a wonderful opportunity for some calligraphy. I hope you enjoy calligraphy. Here we go with some fun calligraphy. Yeah, that was pretty good. I tensed up here at the end. That you can tell by analyzing calligraphy. You can tell I tensed up right there. But it's supposed to be very free-flowing capital L written in cursive. That's the Lagrangian. Okay? Q dot T. Okay, so this comparison table is very helpful to us. Currently, we're in chapter 6. In today's lecture, we're going to continue very intensive study of chapter 6. And you're working on homework 2 right now. We mustn't miss a beat here. We got to incessantly work on homework in this course over the summer. There can be no let up. You have to be, it's all or none. You got to be all in here with the homework. So yeah, we're working on homework 2 right now. We're doing this chapter 6 mathematics stuff. Okay, but look at where this is going. In chapter 7, we're going to formulate physical theories. Remember in chapter 6, we're doing variational calculations, which is a very broad umbrella term. Sometimes people speak of minimizing a surface area. If you have a funny shape of wire and you dunk it in some soapy water, pull it out, you have this surface. The soap film minimizes the surface area. Remarkably, it can find a three-dimensional surface whose boundary is prescribed. It must be the wire frame, okay? And whose area is minimal. This is an example from chapter 6, the calculus of variation, okay? This is more abstract mathematics. Sometimes we'll be talking about a farmer who has some fencing material and would like to enclose as much land as possible, given the presence of a cliff, which provides essentially a free boundary to the parcel of land. What's the best way to enclose as much land as possible? In chapter 7, we're going to be looking at a variational formulation of mechanics. And there we'll focus our attention on this Lagrangian, basically the kinetic energy minus the potential energy, okay? The crucial thing is we now recognize our familiar setup for mechanics problems. We have time as the independent variable. And if you're solving a one-dimensional problem, it's x of t, okay? So this allows us now to get a better understanding. How can it be in chapter 6 that y and y prime are independent variables? Well, we can answer this now using our knowledge of physics, right? So it is, it's our knowledge of physics together with the understanding that there are different contexts, okay? So let's talk about, we'll say a few remarks here about chapter 7, okay? In particular, let's have a look at this x of t. Yeah, the blue pen is fading. It's seen better days, but I like to keep it around. This tells us we're going to talk about x of t for a second. Okay, so what does that mean now? We're talking chapter 7, we're doing physics. This means you have a one-dimensional problem, a particle moving along a one-dimensional axis, and the solution is a function. Your goal in life in mechanics is to find the solution, and that's x as a function of t, okay? But notice the Lagrangian right? As you know, in physics, we use the dot for time derivative. The Lagrangian is a function of x, x dot, and t, and these are viewed as independent variables. This is crucial, and now we can use our knowledge of mechanics to really appreciate that statement. So I'm going to emphasize you see those three arrows? They are pointing at three independent variables. Independent. Okay, and let's talk about the context. All right, so this thing here is going to be one thought bubble, the context. Okay, so I drew a big blob there. If we say that x and x prime, sorry, x dot, x dot, this is the position, the velocity, and the time t. The context is that at one instant, okay? And think, for example, when we talk about initial conditions, we know in mechanics, in classical mechanics, the evolution of the system is determined by the initial conditions, okay? So we're talking about, if you want to solve for x of t, your goal is to find this function. And here, clearly, x is a function of t, and x dot, when you have the function, x dot, okay, so when you solve the problem, and get this, let's draw another blob here, solution. So when you solve the problem and get the x of t, then x dot is simply the time derivative. It's dx dt. Okay, so this is a separate blob. It's a different context. Okay, and this is the important thing. We have these two different contexts. So again, when you solve the problem, you get a function, x as a function of t. That's your solution to the problem. And then it's true that x dot is the derivative, okay? But at this stage, this is an earlier stage in the discussion. We have three independent variables. And so the context here is at one instant. For example, we have the notion of the initial conditions. All right. And you know from laboratory experiments, right? You as the experimenter, you choose the initial position of the particle, you choose the initial velocity, that determines the classical state. The subsequent evolution of the system is determined by the classical state. So it's very clear, especially with this phrase initial conditions, at some time t that you choose, you can specify x and x dot independently, okay? And various functions, we're going to talk about the Lagrangian, we'll talk about the kinetic energy, we'll talk about the potential energy. These functions are functions of these variables. Usually the potential energy does not depend on x dot. Okay, so that's kind of the big picture. And this table kind of shows you where we're going. The important thing for us right now is the independent variables. So red ink. I know the red ink is a little bit hard to see, but I'm holding the red. The red pen has a brilliant red color on the handle and the clip. There's no question this is red. In some sense, all of this discussion, this big table, all this stuff was to appreciate this statement here, that x, x dot, and t are independent variables when we're talking about the Lagrangian. And when we're setting up the variational principle, these are independent variables. Later, when we solve the problem, then x dot as a function of time is the derivative of x as a function of time. Okay, great. So now let's resume our discussions. As we go through this, we'll take opportunities to make remarks about homework number 2. And of course, I will be publishing some more hints because I know it's a difficult assignment. Okay, so last time we talked about a famous historical problem. This is one of the crown jewels of the calculus of variation. Basically, this problem with the Brachistochrone, how do you design a roller coaster that will get you, it will transport some people. I mean, they paid their money to get into the amusement park. You want to transport them as quickly as possible from the starting point to some location in the roller coaster. Famous problem. Another one, the catenary. If you take a chain and suspend it, okay? So you can think of a suspension bridge, etc. Nice image from some classical architecture. But simply a chain such as in a jewelry store, they also have these nice gold chains, right? If you suspend a chain between 2 points, what's the shape? Okay, that's the problem of the catenary. Again, another famous problem. It wants to minimize its potential energy. It's not a dynamical problem. Remember the roller coaster, we do have some dynamics. You have a car rolling down these tracks. There's certainly time dependence, et cetera, and so forth. But for the problem of the catenary, you simply have a static chain. The chain wants to minimize its potential energy. You could grab one of the links and pull down and lower its gravitational potential energy, but then other parts of the chain would raise up. So it's a very interesting trade-off, and it's remarkable. We can use the calculus of variations to compute the exact shape in equilibrium when we have minimized the potential energy, the total gravitational potential energy of the chain. A very nice illustration from the calculus of variations. All right, so again, we set this up in our last meeting, chapter 6. We're gonna skip the setup. And we talked about the Brachistochrone. So at the end of our last meeting, we were talking about the Brachistochrone with the role reversal. So I can point to what we were doing. At the end of our last lecture, we were right here. We were doing chapter 6 material. We had the role reversal. How annoying was that to have this role reversal right away? So let's revisit chapter 6. Once again, we'll look at the Brachistochrone, but we will not do the role reversal. So here we go. Brachistochrone. Okay, and of course this topic is present on the current homework assignment. Homework number 2, you're going to solve, that is to say, you got a job designing a roller coaster on this asteroid. It's a spherical asteroid with no rotation. It's kind of a special asteroid. It has no rotation whatsoever, and it's a perfect sphere. You need to build a roller coaster there, and we want to see what does a Brachistochrone look like in a non-uniform gravitational field, because the size of the roller coaster is becoming comparable with the size of the asteroid. Here on Earth, we're living on a huge planet. Designing a roller coaster here, we can simply assume a uniform gravitational field. Good old G, you know, the lowercase g vector pointing straight down. To high precision, you can assume this is a constant vector. And this is the traditional problem of the Brachistochrone. So let's solve this problem again. And this time we will have x as the independent variable. And we will compare this with what we did last time. X okay, so what does that mean? Again, let's look at our table. This is the usual, the first row in the table here is a summary of the notation in chapter 6. If you look at the chapter summary, I will emphasize it here. Have a look at the chapter 6 summary. Okay, if you look at the chapter 6 summary, might as well write chapter 6 summary. Yeah, if you look at the chapter summary, this is the notation. So this is the language that is spoken in the chapter 6 summary. Okay. Unfortunately, when the Brachistochrone problem is first introduced in chapter 6, we have the role reversal. But we know part of life, when you do physics, you may look at different references and you may look at different books. Different authors will write different papers and people use different notations. So we have to be able to adapt. We have to have this adaptability. Okay, so what we'll do now is solve the Brachistochrone using the usual, this is the usual state of affairs here. This first row, x is the independent variable, y is the dependent variable. Okay, so here we go with Brachistochrone. The takeaway message is the following. Okay, so this is the usual, this pen, perhaps not the best. All right. We have f as a function of y, y prime, and x. And again, this is the usual state of affairs in chapter 6. You want to have an f function that's a function of y, y prime, and x. Let's understand that our f function here is now the following. One plus y prime squared, and now downstairs still inside the square root over y. Okay, we'll go through the picture. You know, we'll draw the picture. We'll go through the calculation and prove that this is our f function. But let's appreciate that y, this variable here, occurs in the denominator. Y prime occurs right here. There's no explicit occurrence of x. Okay, let's understand how that comes about. All right, so we're going to draw the picture that we had last time. Okay, so here we go. Let's draw the picture of the Brachistochrone. Okay, there are the axes. So x, that's a horizontal x-axis going to the right. Y is going straight down. So the gravitational acceleration points in the positive y direction. We're going to release the roller coaster car from here. We have this very special shaped roller coaster track, which achieves the goal. We're going from location number 1 over here to location number 2. This is the fastest way to get there. You could try a straight line, it's going to be slower. Even though the distance is shorter, it's slower. Right? Again, the key here is because this very dramatic drop at the beginning, we gather much speed early. That's the key to success here. But not too much. You wouldn't want to go vertical way down here and then try and get over there. That would be counterproductive. Now the path is too long. So very interesting trade-off between gathering speed early. This is the physical intuition. Gathering speed early, yes, that lengthens the journey a bit, but then you go careening over here. Everyone's cheering and they're happy. You know, they wave their arms in the air because of the Brachistochrone. Okay, so let's understand the setup. We look at a differential portion. All right. And as always, the endpoints in this discussion are fixed. So that location is fixed. Number 1 is fixed. Location number 2 is fixed. We're going to add up the total transit time. So here's a differential installment along the journey. Okay. The question is, how long does it take? What's the dt? So the total time getting from location 1 to 2, it's an integral of dt. That's the simplest way to put it. We're going to add up all these differential contributions, going from location 1 over to location number 2. So I should put circles here. This should not be taken to mean t equals 1, and this is not t equals 2. So I'm putting the circles there to just say these are points in space. All right, so this is rather abstract notation. Okay, and then we're going to integrate. So what's dt? Well, it's the distance. There's a differential distance there. That's a little s. And then you divide by your speed. That's v. Okay. And then we've been through this before. The ds is the square root of dx squared plus dy squared. Okay. And now since we're choosing x as the independent variable, we're going to factor out that dx. So ds is dx, and now we got 1 plus y prime squared there inside the square root. Okay, wonderful. So, and then, so this is equal to a constant, right? Remember, we used the conservation of energy to show that the speed was proportional to the square root of y. The multiplicative constant does not concern us because if you want to minimize the time, it's equivalent to minimizing some constant times the time. So we'll drop that. And just remark here, there's a constant which we don't care about. So I'll put constant. And then we have this integral of this thing here, the square root Okay. So I kind of had to squeeze it in there. All right. So the purpose of this discussion was, again, to exercise our understanding of how you set up a problem. There's a quantity of interest, right? There's a quantity of interest. For this particular problem, the quantity of interest is the time it takes for the particle. You can think of a bead on a wire. It doesn't have to be a roller coaster. This could be a bead sliding along a wire. That's the way it's often phrased. So for home experiments, you should probably use a bead sliding on a wire and then get these stopwatch out and measure how much time it takes sliding down like so. Okay, so we set up the integral, and the crucial thing is we must phrase it like this. The emergence, right? The emergence of this function, and let's just observe like this. So that function f is really at the heart of this. Oh, wait, we got a question. I just looked at the chat window. Let me see. This was at 112. Okay. I was worried I had snoozed too long. Where does the 1 over square, great question. Where does the square root of, what's happening there regarding that square root is the following. Because we start from rest, okay, we have the following conservation of energy. Okay, we're starting from rest here. So we have a very powerful statement. The kinetic energy at any location throughout this journey, we can say the kinetic energy 1/2 mv squared is equal to the gravitational potential energy liberated. So traveling from this location to a lower location, that frees up some GPE, gravitational potential energy, and the value is mgy. And the reason is the y coordinate is precisely a measure of how far lower you are. What's the reduction in elevation? That's precisely this y coordinate. So this is the equation. There's no need for a minus sign or anything like that. This g here is the usual positive 9.8 meters per second squared. Okay, and now we can clean up a bit. We can cancel off that m. And we've got v squared equaling 2gy. Okay, so this is a very powerful principle. Along this journey, we can say, no matter what shape, you know, you as the roller coaster designer, you are free to design a roller coaster of any shape. Regardless of the shape that you choose, it's always going to be true that the square of the speed, this v squared here, is equal to 2g times your drop in elevation relative to the starting point. Okay, So this v, there's a little lowercase v here, that's the speed. That's a constant times the square root of y, and that's the square root of y here. Okay. So now let's take these various discussion points and bring them all together. And let's do the following. We set up the problem for the Brachistochrone, and we looked at two different ways to set it up. So I'll write that here. Okay. Again, the problem of choosing the shape of this roller coaster. Okay. Here's what we saw. If you choose y as the independent variable, okay, this is what we did at the end of our last meeting. If you choose y as the independent variable, then we see the following. Okay, this was the so-called role reversal. And what we learned last time is we have an f of x prime, y, and that's going to equal this square root. There's a numerator with a 1 plus x prime squared, like so. Okay. And now you also have the alternative, choose x. This is what we did today. We kicked off our meeting today by choosing x as the independent variable. Okay, then, what did we learn? We've got this f, and the nice thing is, this is the usual notation. If you look at the chapter 6 summary, this is the notation. That's why this is really, for greater clarity, we should focus our attention on this one. Okay, but we're going to see that both of these will tell an interesting story because there are some more powerful principles that are going to emerge here. Okay. Okay, so there you have it. This typically, and also thinking of exam problems, this is typically one of the most difficult parts is setting up the problem, and the problem will necessarily involve an integral for some quantity of interest, and then figuring out what the f function is. Again, for any given problem, you'll have a different f function. Later today, we'll talk about a farmer who would like to enclose as much land as possible using a fixed amount of fencing material, okay? And again, given the presence of a cliff, which provides a free boundary, it's a straight line boundary for part of the property, okay? So in that case, it's the area. The farmer would like to maximize the area, and that fits into this principle here. We'll set up an integral for the area enclosed with this fencing material, and then we'll invoke the principles here from the calculus of variations. Okay, so the very powerful statement here is that once you have set up a variational principle, okay, and so for the Procristocrone problem, this roller coaster problem, we have a statement. We've computed the time it takes for the roller coaster car, it's a single car, to make this journey, and we'd like to minimize that time. All right, so the prescription now from the calculus of variations is we must compute some partial derivatives. So this is the usual notation. I'll emphasize that here, usual. Right? Normally, oops, I went off the camera. Normally we like to have x as the independent variable. Right? Let's look at our table here. This is the table we talked about a moment ago. When x is the independent variable, this is what we have in the chapter summary, chapter 6 summary. That's the usual state of affairs. Okay, and then we have a very clear prescription. The first order of business is to compute two partial derivatives. So compute. We must compute some partial derivatives, and that means differentiate with respect to one variable while holding the other variables fixed. Okay, so here we go. We're going to compute the partial derivative. Okay, just a second here. Let's not scramble up the notes here. We're going to compute partial f, partial y. Okay, so we have our work laid out before us. Right, that's the nice thing about this calculus of variations. Once you have figured out this function f, then you have a very clear prescription for what you must do. Here, we must compute the partial derivative of f with respect to y, and we must compute the partial derivative of f with respect to y prime. Okay, so here we go. There is an occurrence of y right there. What do you know? We got ourselves a y. All right, so notice the story was different last time, right? Last time we had a different story. We'll get back to that. But here we are looking at this function f. We have y raised to the power minus 1/2. If you differentiate y raised to the power minus 1/2, it's a minus 1/2 y to the minus 3/2. And then this numerator, this is simply a constant, because for this partial derivative, y prime, which is an independent variable, is viewed as a constant. Okay, great. Now, the other question is, what's the derivative of f with respect to y prime? So now this thing here, the denominator, the y in the denominator, that's a constant. We must differentiate. So let's simply write the y to the minus 1/2. This is a constant. It's a multiplicative constant, y to the minus 1/2. And now we're faced with differentiating this expression to the 1/2 power. So this is a 1/2. The expression to the minus 1/2 power, that's a 1 over the square root. Okay. That's not y to the 12th, it's y prime squared. And then we must differentiate what's inside. The chain rule tells us we must differentiate what's inside the square root. And that 1 is a constant, but we do get 2y prime. So we multiply by 2y prime. Okay, now the remaining task is to compute a total derivative. Okay, so this gets a little bit tricky, right? So we're going to compute the total derivative. Okay, and let's take a second to remind ourselves where this came from. All right, the Euler-Lagrange equation. Okay, so I'm going to be very careful on this piece of paper. Notice we have a side-by-side comparison. Always very useful to have a side-by-side comparison of two things. Over here, we're studying this problem using the usual notation, and we've chosen x as the independent variable. So I'm drawing this dividing line here. The entire right half of the paper is devoted to this analysis here using the usual notation. So then compute. Okay, so remember the first step is you compute these partial derivatives. Then we must compute a total time derivative. That's kind of the prescription. Then we're going to start talking about some shortcuts. Often there are some very nice shortcuts that save you a huge amount of effort, because we're going to see these calculations can get messy rather quickly. And for the current homework assignment, homework number 2, I will publish some hints that explain how to avoid some very unpleasant, lengthy calculations. We want to avoid the tedium, because that's no fun. Okay, so the Euler-Lagrange equation, in the usual notation, I want to emphasize this stuff is the usual notation, the notation that you see in the chapter 6 summary. That's at the end of chapter 6. Okay, we got the partial of f with respect to y minus the total derivative, partial f Okay, so it's written like this. A question that students often have, well, if there's a minus sign, can't you just move this term to the other side? And the answer is yes, absolutely. You could write that partial f partial y equals the total time derivative of partial f partial y prime. That's true. The reason it's traditionally written like this is there's a whole other topic called Lagrange multipliers. That's something we'll talk about later. But if you introduce Lagrange multipliers, then you get something non-zero over here. So this is kind of a reference. The tradition of writing the equation like this is kind of a reference to the fact that if with the inclusion of Lagrange multipliers, you do get something non-zero over here. Okay, but the really important thing for us right now is to appreciate the functional relationships. And remember, when we started the course, we really took some time to look at the relationship between multiple variables. We talked about problems with 2 variables, problems with 3 variables. When you have 3 variables, you have to talk about partial derivatives. You're computing derivatives. We got a problem with the document camera. Something happened to the document camera. Okay. This is not good. There's a message. Yeah, this, you know what, this happened last year. What happened is there's a notification, your Apple ID, because this is an iPad Pro. This document camera is an iPad Pro. Somebody in San Jose is using this, and that's actually to be expected because the physics department is using the same account for all of these iPad Pros that are distributed. Okay, so here we go. We're going to click OK. The host, okay, another notification. The host has spotlighted your video. Would you like to join audio? No, that's what I told you when I first set this up. So now it will flip over the ping pong table. Okay, here we go. Okay. Yeah, so we're up and running here. A little unpleasantness. I did talk to the director of instruction about this. If somebody does something with an Apple ID in San Jose, it pops up a dialog box here and it kind of trips up our lecture. Okay, a little comic relief. So, yeah. The functional relationships. We got these partial. Notice the notation down here. This is the partial derivative of f. That's why we have the special script D there. Partial derivative of f with respect to y. Partial derivative of f with respect to y prime. So this equation here, this is the Euler-Lagrange equation. Okay, famous equation, 2 famous mathematicians here, Euler and Lagrange. The notation serves as a guide here. So the first thing you do is you compute these partial derivatives, but then you see the ddx, that's an ordinary ddx. And that tells you something. That carries quite a statement with it. What that means is if you have an ordinary ddx, that means you're differentiating a function that is a function of a single variable. That's why we use the ordinary d's. If you have multivariable functions, then you have these stylized d's indicating partial derivatives. But this thing here is an ordinary ddx. We must be differentiating an ordinary, a function just of one variable. So the crucial thing is functional composition. So back to the main plot here, then compute the ddx. Okay, so if we're going to compute this ddx, we must construct a function of a single variable. Okay, yep. And so functional composition, what we do is we compute this partial derivative of f with respect to y prime, we compute that. And remember, f is a function of three things. So when you compute the partial derivative, again, that's a function of three things. Then we must insert, okay? So remember, f is a function of y, y prime, and x, right? So the partial derivative of f with respect to y prime, oops, sorry. The partial derivative of f with respect to y prime is again a function of y, y prime, and x. But now we insert the function y of x. So now we write y of x, y prime of x. Okay, so this is another major milestone in the calculation. And again, this is the transition. Remember at the beginning of today's lecture, we talked about a certain transition. Let's remind ourselves, okay? In the language of chapter 7, when you have the Lagrangian, we have these three independent variables, right? So this entire thought bubble here was, for this context, it is meaningful to talk about x and x dot as independent variables, because, and it's the same logic that governs any experiment when you're talking about initial conditions. These are three independent variables. You choose the time to start your experiment, you choose the initial position and the initial velocity. That defines the initial state, and the initial kinetic energy is defined, and the initial potential energy is defined. That's what's important to us. Later, when you solve the problem, you have a functional relationship between x and t, and then you're welcome to differentiate that, okay? So that's precisely the transition we're seeing here now in this problem. We computed two partial derivatives here. This was in the context where f was a function of three independent variables, and that's the context here for computing these partial derivatives, these two partial derivatives. But the next part of the prescription is to insert. So after you compute this partial derivative, then you insert y of x here, you insert y prime of x here, you insert x here. The resulting object, which is a function only of x, must then be differentiated. Okay, and that is why this chapter 6 is considered to be a very difficult chapter. We have quite a bit of interesting maneuvers. These are interesting mathematical maneuvers, but now we must differentiate. Okay, so we're going to take this thing here. Okay, here we have y to the minus half power. We have a couple numerical factors. They actually cancel rather nicely. Okay, so what we're looking at is y prime. I'm copying this thing here. The 2's have canceled. That's the one bit of good news here. The 2's have canceled. The numerator, we got the y prime. Downstairs, okay, oops. So what I've done is I've simply copied over this function f, but now we must insert the actual trajectory. So that's y prime of x, and down here it's y of x and y prime of x. So to really complete the picture, now we have y prime of x over the square root of y of x times 1 plus y prime of x. That is squared. Okay, and this is the crucial point now. we have to differentiate this thing. And I hope you like calculus because this is going to require some effort. Obviously, we'll use the quotient rule. The numerator is y prime. What's the derivative of that? Well, that's y double prime. Okay, that wasn't so bad. But then we have this denominator. It is a square root of something, and that something is the product of two functions. So this is going to get rather messy. Okay, so the point is, you do get a second order differential equation. You can see when you differentiate this, we observed rather quickly, we're going to get a y double prime. Once you have a y double prime, you've got a second order differential equation. We're going to get a lot of other terms. It's going to get rather messy. Okay, notice down here there's another y prime. So as we work our way through this complicated denominator, attempting to differentiate everything in sight, there will come a point where we differentiate this y prime and get a y double prime. Okay, so this, the takeaway message is we do get a second order differential equation. All right, and now let's look at our summary. If we were in the physics building right now, I would have a different chalkboard and I would say, look at our table. We're going to get a second order, looking at chapter 7 now. We're looking ahead to chapter 7. We're going to get a second order differential equation. That's precisely what we learned, Newton's second law, right? Force equals mass times acceleration. That acceleration is a second order derivative. So in terms of the physics, right, in chapter 7, we're going to start doing physics again. We do get our second order, the so-called equation of motion, the differential equation that governs the motion. Okay. So let's look at some techniques because many times it's possible to avoid, right? We haven't even gotten to the differential equation yet. In principle, we would have to grind out this derivative and then we would have our differential equation. And you know, the world of differential equations is rather difficult. The sad reality is that most differential equations cannot be solved in closed form. Only a few can be. So that's again, oh yeah, one more announcement. I was going to say the complications of solving some of these difficult differential equations are yet another motivation for bringing in computers, because a computer can solve this differential equation here just as easily as it can solve the simple harmonic oscillator, right? It's just grinding out some derivatives, time stepping your way through, et cetera, and so forth. So the announcement is we're going to postpone the Python to later in the course, right? The reason is with the summer session, right? This is the first time I've taught the summer session. I have taught the course 11 times, but this is the first time during the summer. It's not, and oh, and the thing with the Python, that kicked in very recently. It seems like just what was last year, I was on those committees working out the Python program. But at that time, there was not an official mandate to have Python in the homework. But now we do have the mandate. Okay, put it all together. The only logical conclusion is that we should postpone the Python to later in the semester. Because right now we're very busy with this chapter 6 business. Very confusing, advanced material, right? Let's not add a layer of grief onto that with the Python. So Python will come later in the course. Okay, so let's talk about some very good news that the second order differential equation can be avoided in many cases, and you can solve a first order differential equation. That's a much happier place to be, a first order differential equation. This is what we started the semester with. We used the conservation of energy to get a first order differential equation, and we could solve for the position as the time as a function of position. So let's see how that emerges here in the context of the calculus of variations. So there are two theorems we're going to talk about. Okay, two theorems, and these theorems are your friends. They will help you through difficult times. All right. Again, our goal in life right now is to solve this Euler-Lagrange differential equation. Okay, very nice equation. This is the very heart. This is the centerpiece of chapter 6. Really appreciating this differential equation. Let's talk about ways that we can simplify this and avoid a second order differential equation. Okay, so we'll talk about two theorems. Okay. These are theorems that simplify the task, this extraordinarily difficult task of solving these differential equations. So theorem number one, if the partial derivative, and everything we're doing now is in the usual notation of chapter 6. So when I say the following, if the partial derivative of f with respect to y this could happen, and we have seen this happen, right? If the partial derivative of f with respect to y is 0, then there's some really good news here. Okay, the partial okay, it's a constant. We're going to talk more about this. It's not one global constant. It turns out for different initial conditions, you'll have different constants. But in classical mechanics, one speaks of the orbit. Even if you're not doing celestial mechanics, for any mechanical problem, the time evolution of the system is called the, quote, orbit of the system. So along any orbit, you have this constancy. It's a different constant for different orbits. Okay, so let's prove this. Well, we can prove this rather handily. It actually follows immediately from our theorem here. So here we have the Euler-Lagrange equations. Now remember the assumption here for theorem 1, if this partial derivative is 0, and that occurs right there. If we have a 0 here for this partial f partial y, well, the remaining statement is that the derivative of a function is 0. Well, then that function must be a constant. So calling this a theorem is a little bit, we're being a little over dramatic here. It's not that amazing of a realization, but it's still very useful. This equation is a first order differential equation. That means you have only first order derivatives. Okay, so, and let's talk about another theorem, Theorem 2. This one is going to be more sophisticated. But both of these theorems empower you to simplify the problem, okay? Theorem 2, okay, and again, we're using the standard notation of chapter 6, if partial f okay, what if partial f partial x equals 0? Well, then there are some amazing things that happen. Let's investigate the amazing world that emerges for us here. Okay, let's begin by computing a total time derivative. Okay, this will be a nice exercise to remind ourselves, what does it mean to compute a total, sorry, I spoke the language of chapter 7, right, because that's at the heart of the mechanics. In chapter 7, we would say a total time derivative. Here, when we have this in the Euler-Lagrange equation, this d dx, this is called a total derivative. It's not a partial derivative, right? So you can see where the terminology comes from. A partial derivative, you differentiate with respect to one of the coordinates. This ordinary d dx indicates a total derivative. That means you take whatever you're differentiating. In this case, it's partial f partial y prime. You insert the orbit, the function y of x, y prime of x. The resulting object is a function of a single variable, x. And then the derivative is denoted with this notation, d dx. So this is called a total derivative, all right? So this will be a useful exercise. Here we go. I put ... because we're going to have to do a couple maneuvers here. Let's start by computing the total derivative of the function f. Okay, notice it's extraordinarily important that we're clear on the notation. This thing here is the partial derivative. The function f is a function of three things, right? It's a function of y, y prime, and x. And this is the partial derivative. So we're viewing those three things as independent variables. We're holding y and y prime constant. We're differentiating with respect to x. Okay. Later in chapter 7, again, that's where we do physics. This theorem number 2 will have some physical interpretation. If the Lagrangian is time independent, if there's no explicit time dependence in the Lagrangian, then the mechanical energy is conserved. That's a wonderful physics statement, right? If the Lagrangian is time independent, then the total mechanical energy is conserved. And you know those conservation principles, we've been using those principles since the beginning of this course. The conservation of energy enabled us to avoid second order differential equations at the beginning of the course. We wrote down some solutions for the evolution of the system because we had reduced it to a first order differential equation and a first order differential equation that we could solve via integration. Historically, that was solving by quadrature. That's a historical term. Okay, so let's emphasize this partial derivative is assumed to be 0. This is a completely different beast. This is the total derivative. Let's be very clear. What is this? It's the derivative with respect to x of the following function of x. Okay. Yep, so we have to differentiate this. Notice, and we'll use completely standard calculus. We have a very interesting object here. Notice we have 3 occurrences of x. No problem. We know what to do. We're going to use the chain rule. We must look for any occurrence of x and we must differentiate. So there are 3 occurrences of x, and here we go. The chain rule tells us, how do you differentiate something like this? Well, there's our first occurrence of x. So we get a contribution. There are going to be 3 terms in this derivative. We have the derivative of f, and that's a partial. So partial f with respect to its first argument, the name of that argument is y. And then you must multiply, the chain rule says you must multiply by the derivative of whatever is there. Well, there's a y of x, and now that's y prime of x. Okay. Now here's another occurrence of x. So we have plus. The chain rule tells us you must differentiate, and this is a partial derivative, differentiate f with respect to its second argument. The name of that argument is y prime. So that's a partial f, partial y prime. And then we must multiply by the derivative of that second argument. That's the chain rule. So we must multiply, in this case, by y double prime of x. And then the chain rule says there's another term, the derivative of f with respect to x. Well, that's the one we assumed was 0. So I'll put plus 0. Right? Isn't it neat how we got to use this? This is our assumption here. For theorem 2, we're going to assume partial f partial x is 0. That's precisely what was vanishing here. Okay. So now we'll have a look at the Euler-Lagrange equation. Okay, and we're going to recognize this thing here. This is equal to, okay, the derivative with respect to x, all right, of a product. And let's appreciate this product. Again, this is a total derivative with respect to x. So all the words we have said, again, come to bear here. We're going to compute this derivative of whatever's in here with the understanding that you have manufactured a function that is only a variable of x. This is accomplished by inserting y of x and y prime of x wherever necessary. So let's have a look at the total derivative with respect to x of partial f, partial y prime, y prime. Okay, so there's some effort here. Let's go through this very carefully. It's possible to get derailed into a calculation that gets messy and yields no forward progress. So let's be very careful as we go. We're going to use the product rule because this is the product of two functions. Whatever craziness is going on with the functional composition, that is to say, we're going to be inserting things into this partial f, partial y prime. That doesn't change the fact that we have the product of two functions. So when you differentiate the product, one of the terms will be when the differential operator operates on this y prime. That gives us the y double prime, and you copy over the first factor. So we see that the product rule for differentiation here gives us this second term very quickly. Right? There's not much difficult stuff to be done there. You simply use the product rule, and you know there's going to be a term where you differentiate the second factor and leave the first factor alone. That's precisely this term here. Okay. The remaining question is, what happens when you have the total derivative with respect to x acting on this partial f, partial y prime? You could, in principle, do something like we did earlier in the calculation, but it's better not to. It's better to use the Euler-Lagrange equation, because you see, when this differential operator acts on the first factor, that's precisely what we have here, right? This term, d dx, and we know that's equal to partial f, partial y. Okay. And so you see, for that one, you copy over the second factor. That's this y prime going right there. And then this partial f, partial y is coming from the total derivative with respect to x acting on that one. Okay, so we have this. And so now we can subtract this thing and this thing. We see that their x derivatives are equal, so the difference has a 0 x derivative. So then here's the wonderful conclusion, d dx, and we'll put big old square brackets here, the f minus this thing. Okay, so the derivative of this thing is 0. Therefore, this is a constant. So f minus y prime partial f partial y prime is a constant. And this is the wonderful conclusion here. So both of these are wonderful results. Remember, Theorem 1 gave us this. This is a first order differential equation. Wonderful. So anytime you have a problem where partial f, partial y is 0, that's great news. You can breathe a sigh of relief. We have this. Theorem 2, a little more complicated, but if you have a problem where partial f, partial x is 0, there's still some good news. It just requires a little more work. And you can just use this result now that f minus y prime, you see the units work out fine, right? Whatever dimensions f has, this second term will have the same dimensions because you have y prime times the derivative of f with respect to y prime. So that's a constant. Okay, okay, we have a question in the chat window. Let me scoot the chat window over here so I can. Oh, we have 2 questions. Yep, just in the last minute we got a couple of questions. Okay, so first of all, are we assuming partial derivative of f with respect to x is given as 0? Yeah, for theorem number 2, this is the assumption. Okay, so the question at 1:52 p.m. was, are we assuming the partial derivative of f with respect to x is given as 0, or are we going through this calculation? Yeah, great question. So here, it's important to be clear on the logic. So Theorem 2, this is the hypothesis for the theorem. So this theorem can be used anytime partial f, partial x is 0. Then we have this wonderful conclusion. In the language of mechanics, we'll have a constant of the motion. In chapter 7, we're going to see that this gives us the total mechanical energy. It's not very clear right now, but we're going to get the total mechanical energy. And again, the wonderful result from chapter 7, if the Lagrangian, we're talking about the Lagrangian formulation of mechanics, if the Lagrangian function is time independent, if there's no explicit time dependence, of course there's implicit time dependence because when you insert the orbit, it has a time dependence. But if the Lagrangian has no explicit time dependence, then the total mechanical energy is conserved, and that's what we're gonna get that from this theorem too. Okay, there was another question at 153. Just to clarify, this is all with the assumption that F is independent of X. Yes, that's right. Great point. And again, that was the same as what the two questions were both privately sent to me, and they were independently expressing the same thing. Yeah, this theorem number 2 has a hypothesis, partial F partial X is 0. Theorem number 1 had a different hypothesis. This was the hypothesis for theorem number 1. Okay, so let's talk about where we're going with this. We have the problem of the Procristocrone, right, which was designing this optimal roller coaster that should really maximize profits for the amusement park, because think of all the mathematicians that are going to travel from across the globe to get to ride on this thing. Yeah, the Brachistochrone. We had the two formulations of the Brachistochrone. One of them had X as an independent variable, and the other one had Y as the independent variable. So for these two formulations, it turns out in one case, theorem 1 saves the day in the sense that you avoid a lot of unpleasant work. In the other case, theorem 2 saves the day. So as you read chapter 6, right, and again, it's essentially that you do the reading assignment. Let's not worry about the solution. Remember, the machinery that we have in place here in chapter 6 is a machinery. The big picture is you have a variational principle. If you're doing optics, it's Fermat's principle of least time, that a light ray will find, usually it's the quickest way, the least amount of time to get from one point to another. And using this, you can explain refraction and all these wonderful optical systems. So there are variational principles throughout physics, and recently we saw a very nice presentation. I showed you a couple slides from a presentation using variational principles to analyze these remarkable machines, right? We have a remarkable accelerator physics going on right next to the Berkeley campus. You've got Lawrence Berkeley National Laboratory. And of course, our friends across the bay. Sometimes for the big football game, people would have you think they're our enemies, but they're our friends. Stanford, they have the Linac coherent light source. That was the world's first X-ray laser some years ago. And now there's the LCS2. That's a Roman numeral 2, an even more wonderful machine. So a lot of the people that I worked with at LBL, they migrated over to Stanford to work on this phenomenal accelerator. And you can look at their website. They have a certain schedule. In August, they're going to start again with another run producing ultra-fast X-ray science. So variational principles are useful in theoretical physics for all kinds of problems. And here in chapter 6, with the Brachistochrone, don't worry about the details of solving the differential equation. We get some interesting differential equations, and the book presents the solution, right? The cycloid, that's another classical curve from classical geometry. There's a little bit of effort of solving the differential equations, but really the takeaway message here is that when you set up a variational principle, okay, so you set up a variational principle, the idea is you have a variational principle and you find this function, what we've been calling lowercase f. Let me just clean up a little bit and move the chat window. Oh, wait, we got another question. We got another question in the chat window. Okay, this was a continuation question. Okay, the term in the square brackets. Yeah, the term in the square brackets. So what happened here is we had the derivative of this equaling the derivative of this. Okay, so then we put this on the other side with a minus sign. Okay, yep, so the basic, yeah, great question. The basic premise is that we have a function f. All right, yep, so where did this square brackets come from? The assumption is we have a function f, that's a function of y, y prime, and x. And we showed if this is true, and if the Euler-Lagrange, right, we use the Euler-Lagrange equations here. Right, in this transition, going from this line to this line, we use the Euler-Lagrange equations, because we wanted to argue that when this differential operator operates on this product of two functions, obviously we generate two terms. One of them immediately gives you this term. The other one gives you this if you have the Orla-Lagrange equations. So there were two assumptions, the vanishing of this partial derivative and then the Orla-Lagrange equations. The upshot was we showed that the total derivative with respect to x of this was equal to the total derivative of this. So now we just move this to the left-hand side with a minus sign. It must be that the total derivative with respect to x of this square brackets is 0. Yeah, great question. Okay, so what I'm going to do, I'm going to stop the recording. I'll stay here to answer more questions, but let me just, this requires me to resize the window and click like so.